Here we are with Unit 5, Lesson 7, Connecting Representations of Functions. So this is the last lesson in the packet that you currently have, which means that we're ending the first part of our work with functions and learning about how functions work together and how they interact and just exactly what a function is. Today we kind of wrap that up, and we're going to connect tables, equations, graphs, and stories of a function, seeing how they all come together into one. Before we get going with this, here's three different ways to represent a function. First off, we see an equation, y is equal to 2 times x. And then we see the graph of the function, where we recognize that, again, the graph is proportional. It's going through the origin. And we see that when we talk about y equals 2x, we see that y is equal to 2, and 2 times 1, 2 times the x value is 2. And then finally, we see a table. So the question is, how are they alike and how are they different? I think, let's see if we can get all these on here. If we're talking about how are they alike, I would have to say some things like the equations for the first two would have the same form but different variables. So when we're talking about this one right here, the variables are going to be a and b. So we would see this one would actually end up, when we write it, we would say b is equal to 2 times a. Perhaps didn't catch that in the very beginning, but that's how that one works. We could say that the graphs for the first two are identical, except for the labels on the axes. So these axes would be x and y, and these axes are a and b. Could also say that the table of values right here for both the equation and the graph could have the exact same ordered pairs, but the variables would be different names. So we could change this and call this one x and y, or we could call it a and b. Possibly the third one, the table, has opposite outputs for the same input as the first two. So the graph would be a line reflected across y-axis as compared to the first two. So a lot of different ways that we can interpret the information. The fact is, on all of these, there's still an input and an output. We still have the input on the x-axis, the output on the y-axis. And within a table, we see the input is always in the top and the output is on the bottom. So what we're going to do next here in 7.2 is we're going to compare temperatures. We have this graph of the information and a data table that we will be using to gather data and interpret some data to be able to answer just a few questions on the next page. So I'm going to keep flipping back and forth between the two. The very first question that's asked right here is, which city was warmer at 4 o'clock p.m.? And when we look at these cities, here's one of the cities that has the graph. That's city A. I forgot to mention that. I'm sorry. This graph is of city A, and this graph is city B. In city A, the temperature at 4 o'clock p.m., if we look at time in hours afternoon, here's 4 o'clock. The temperature here appears to be about 57 degrees. And that would be 57 degrees Fahrenheit. And then if I look at this other one, I see the hours since noon. There's 1, 2, 3, 4 o'clock. And so I would see 62 degrees. So city B is equal to 62 degrees Fahrenheit, which means city B is warmer. Cool. Which city had a bigger change in temperature between 1 o'clock and 5 o'clock p.m.? So when we look between those two times, between 1 and 5, it looks like between 1 and 5, we're talking just a little bit more than 50 degrees Celsius or Fahrenheit, to 58. So we have at least 7.5 degrees of change. An increase of 7.5 degrees Fahrenheit. City B, let's see what city B did. For city B, looks like we're going from 1 to 5. We went from 82 degrees to 58 degrees. Well, that's quite different. We see that it decreased by, what is that? That's 24 degrees. So we could see city B went down by 24 degrees Fahrenheit. That got pretty cold. That's kind of surprising to me. What we would say with this one then is we would say city B makes the biggest change because we're looking at decrease of 24 degrees. I'd say probably stay out of that city if you don't like cold weather. All right, how much greater was the highest recorded temperature in city B than the highest recorded temperature in city A during this time? Let's look at city A, the highest temperature. Looks like the highest recorded temperature was 59 degrees Fahrenheit. In city B, the highest temperature here, 82. Looks like 82 degrees was the highest. So 82 degrees Fahrenheit. How much greater was the highest recorded temperature in city B than the highest in A? So we'd have 82 minus 59 is 23 degrees. So we would say that there's a 23 degree difference between the two cities. So compare the outputs of the function when the input is 3. If we're talking about the outputs of the function, the input is 3. The first function, city A, when the input is 3, the output, I just broke my lid. When the input is 3, the output is just a little bit less than 55. So we'll go ahead and call that one just 54.5 just to estimate it. And then when we look at city B, when the input is 3, we get 75 degrees. And all we're doing with that is we look at the comparison. Remember, compare in math means find the difference. And so I would take 75 minus 54.5, and that's going to equal 20.5 degrees difference between the two cities at 3 hours. So basically at 3 o'clock, there's a 20.5 degree difference. Pretty significant. Now you might be looking at all this information saying, why are we doing this? Well, as a function or as functions, the whole purpose is to be able to represent information in a lot of different ways. And with that information, we can gather that information to interpret those pieces of information to make some decisions, such as one city has a much more moderate temperature over time, whereas the other city has some pretty significant changes. You look at just this city right here, from 1 o'clock to 6 o'clock p.m., that's a pretty significant change, moving from a high of 82 all the way down to a low of 58 degrees and 59 degrees. Whereas the other city starts out at 50 degrees or just a little above 50 degrees, gets up about 9 degrees. There's not much of a change in temperature there. Whereas this other one is changing over 20 degrees difference. That's quite a big difference to look at the two places. I would say this one could easily be a desert towards the wintertime, and this one could possibly be more of a moderate temperature, or something that's more like Seattle or something in the wintertime. All right, looking at the next section, comparing volumes. This is an activity that will allow you to actually kind of play a little bit with the Desmos calculator that's there. This section is meant to allow us to take a look at an equation and a graph of volume of two different objects, and then we compare the inputs and the outputs of the functions. And the one function that we're looking at is talking about a volume of a cube with the side length s is given in the equation v is equal to s to the third power. And then we have the volume of a sphere that is given as a function of its radius or in the graph of this relationship is shown. So when we talk about it, this graph represents the radius. The other graph that we can lay on top of this is representing the volume of a cube, so something to the third power. What I'd like for you to recognize is that this is also on a Desmos calculator. There it is. Okay, and on that Desmos calculator, it's all right here. The link will be here into the daily tasks on Google Classroom. But this is an opportunity for you to go ahead and put in and play with these different functions that are going to be given. Please take note that the volume V, it gives all that information above. And we have the 3 questions, 1, 2, and 3, that are given right here, the same 3 questions that are given on your pack or in your packet. But here's the deal. If you're going to use the applet, you have to understand that V, we're going to use Y instead of V and X instead of S. So with the first question, it says the volume of a cube with side lengths S equals 3. So instead of V, we'll put Y is equal to 3. But now I have to figure out how to hit the third power. In the Desmos calculator, when you click right here, the keypad, this brings up several tools for us. And when we want to put in a power, such as the third power, we'll push this A to the B power. And that gives us a supertext, raising it up to the exponent part, put in 3, and then we hit enter. And then drop our keyboard down. What you'll notice is that a red line has appeared here. That red line represents the volume of that cube as compared to the volume of the blue line, which represents the volume of the sphere. And so when we compare these two, it says, is the volume of a cube with side length S greater or less than the sphere with a radius of 3? Well, the radius of 3, if we zoom in just a little bit, will bring us to 3. And we recognize that when the radius is 3, the volume of that sphere is actually over 100 cubic, what is this? What is measured in? 100 cubic units. And so that volume is quite a lot greater. So no, the answer in this one is the volume of a cube with side length 3 greater or less than the sphere. It's definitely much, much less. In this case, what I want to write on here is we want to come up with something that says, possibly we could say less. And then the reason for that, I guess we can end that with a period. We would say that the volume of the cube was 27 cubic, well, units cubed, I think is really what we're after. While the volume of the sphere, I don't know if you noticed on there, said that the volume of the sphere was actually 36 pi units cubed. And it said 3 and 36 pi. And the reason for that, it's well over 100. So when we look at that, and when I looked at that point right here, I clicked on that, and it has 36 times pi. So that would be our units cubed. Let's go ahead and clear that one off, and let's look at the second one. It says, estimate the radius of a sphere that has the same volume as a cube when the side length is 5. So when we look at this one, we would take that volume, remember that we're using Y instead of X, is equal to X, which is 5 in this case. There is another shortcut you can do with this. You can press Shift and 6. It's the caret button that will raise this up to the next power, to the third power. We see that Y is 125. And so our estimate is we'll be looking for this point where the two lines intersect right here. And we can click right on that and see that the volume of that the radius of the sphere would be approximately 1.2, or 3.1, sorry. And we could see that the output is the same total volume. And so when we write this down, take note of that order pair, about 3.1. We can write in here, we could say about 3 1/10. We know that the volume of a cube with the side length 5 gives us a volume of 125 cubic units on the cube, and then the graph shows us the sphere is about the same. The final question, the output of the cube volume function is 8 when the input is 2, since 8 is equal to 2 to the third power. Sorry, I'm thinking about actually what I'm going to write. Compare the output of the two volume functions when the inputs are 2. When the inputs are 2, then what we're talking about is 2 to the third power is equal to 8. And so what we'd have to look at with this is the output of the sphere volume function when the input is 2. If we take this and clear that one, Y equals 2 to the third power, which would be 8. This one is a much, much smaller unit. We can come in here and go ahead and bring this in nice and close, and we can see as we get closer and closer, we can get some really precise values, but we'll be about 1 in 25 hundredths. The volume of the sphere compared to that. Let me read this again. Compare the output of the two volume functions when the inputs are 2. So when this input is 2 for the cube, we get 8 for the output. When we look at 2 on the sphere, we get about 33 and a half or so for the output of this one, or 32 times pi divided by 3. It's kind of a neat tool to play with a little bit more. The final one that we're going to look at, sorry, I kind of wasted some time there. Let's go ahead and just wrap this all up with the last part. Elena's family is driving on the freeway at 55 miles per hour. So we see that distance is a function of time. And then you have Andre's family who's driving on the same freeway, but they're not driving at a constant speed. So their table shows how far Andre's family has traveled D in miles for every 10 minutes. So we're talking about miles per hour versus miles per minute. So how many miles per minute is 55 miles per hour? When we look at this, y is equal to, we know that Elena's family is going 55 miles per hour. So if we're going to talk about miles per minute, we need to take that value and divide, representing y per minute is equal to 55. Just kidding. We want to take that 55 and we want to divide that 55 by 60. So 55 divided by 60 is going to be about 92 hundredths. So we want to take the distance of 55 divided by the time of 60 to give us approximately 92 hundredths miles per minute. We want to take it as a constant rate with that piece. Okay. So who traveled farther after 5 minutes and after 10 minutes? Well, if we're looking at for 5 minutes, if we talk about the crew with what we're after, 5 times 92 hundredths is equal to 4 6/10. If we look at the table and we compare that to Andre, so this right here is Elena, and we look at Andre's family, after 5 minutes, they've gone 5 1/10 miles. So we can clearly tell that Andre's family has traveled farther. And I didn't leave any room for 10 minutes. If I start looking at the 10-minute mark, I can see that 10 times 92 hundredths is equal to 9 2/10. And as we look at Andre's family, after 10 minutes, we're seeing that they went 9 1/10 miles. So we can see that Elena's family travels farther in 10 minutes. So just a mild difference between the speeds. So how long did it take Elena's family to travel as far as Andre's family? Or how long did it take Elena's family to travel as far as Andre's family had traveled after 8 minutes? When we want to look at the two right here, we have to be able to compare the 8-minute value, and we have to compare the 92 hundredths here. So using the 92 hundredths for Elena, that's 92 hundredths miles per minute. We want to be able to bring that in of y is equal to 92 hundredths times 8. And then for Andre's family, this one shouldn't be really difficult. This is 7 8/10 miles in 8 minutes. But when we look at our values, we take 92 hundredths times 8. We get 7 36 hundredths miles. And so we have to consider that piece about after 8 minutes. How far have we gone? And how long did it take Elena's family to travel as far as Andre's family? Oh, whoops, I read that wrong. So how long did it take for Elena's family to travel as far as Andre's family did after 8 minutes? That shouldn't have been an 8 right there. That should have been a 7 4/10 for y is equal to 92 hundredths times x, and dividing that by 92 hundredths. I guess I should show that to you. 7 4/10 divided by 92 hundredths is going to be giving us x is about 8 4/100 minutes for Elena's family to travel the exact same distance that Andre's family traveled in that 8 minutes. So just a little bit longer. You can tell they're kind of coming back and forth with about the same types of speeds. So for both families, the distance in miles is a function of time in minutes. Compare the outputs of these functions when the input is 3. Well, when the input is 3 for Andre, that one's pretty simple to look at. 3 and 3 miles. So at that one, this one, they are going about 60 miles per hour. When we talk about Elena, we have to plug some information in and just use her equation when they're talking about 3. So y is equal to 92 hundredths times 3. So we go ahead and multiply that. Is going to be an output of 2 76 hundredths. So when we talk about 3, 2 76 hundredths, we can see that at 3 minutes, Elena's family is going slower. Andre's family is going faster. So take your pick, whoever you want to travel with. What we can see with that after analyzing all of these is there's not a big amount of difference in their times or obviously for that matter, their speed. And we couldn't have figured that out without having the two functions that are there. While Andre's family is not traveling at a constant rate, it's still a function because all of the inputs have unique outputs. And then we know Elena, even though they are traveling at a constant speed, maybe Elena's family just likes to use that cruise control. Either way, understanding how to interpret the data and how to pull the data out, even with Mr. Quilter's mistakes in here, we can see that the two families are traveling about the same speed. So the bottom line with all this, functions are all about getting outputs from inputs. For every way of representing a function, equations, graphs, tables, verbal descriptions, we can always determine the output for the given input. If we can't, then it's not a function. So let's say we have a function that represents the equation y equals 3x plus 2, where y is the dependent variable and x is the independent variable. If we wanted to find the output that goes with 2, then we can simply put 2 into the equation, find the corresponding values, solve for y, and it must be 8. If we had a graph of that same function, then we could just graph it on there and we could find out, where's 2 on the x-axis, and then 8, we would follow that 2 all the way up until we hit the function and we find out it's 8. If we're looking for a table, then we would look for the input of 2 and find out that the output is 8. With these values, the bottom line is this. If it's a function, I can always find the output for the input. If it's not a function, then I'm going to have problems with it, meaning that the output or that the input may have multiple outputs, and that means that it can't be a function. So that's the end of this lesson. Thanks for checking in. Take a look at the homework. Let me know what I can do to help. Have yourself a great day.